Good morning, all. Over there on my bench is a Berges inverter drive, part number ACM-D2 11.0KW, 11 kilowatts. I'm going to go over here to the transformer. We're going to apply 380 volts AC 3-phase to L1, L2, and L3. Sounds good. Let's get closer. We'll enable that drive to run, and we'll look at the UVW waveforms while we run that light bulb bank. Looks good. Light bulbs are at all the same intensity. Now this drive right here, turn the speed up a little bit. This drive right here we got from the internet. And it was to replace another Berges drive. The oddest thing was when I powered up that original drive, it came up to 1.1 off, and that's normal. But then the dynamic brake was indicated on the display, like the dynamic brake was turned on, DYN brake. And then it would revert back to 1.1 off. And cycle like that back and forth. So somewhere in that original drive, I'll show it to you, it's still in pieces over there. Somewhere in that original drive, something is telling that dynamic brake to fire. A false alarm, of course. Now I put a braking resistor out there, a light bulb bank, and I looked at the BR to plus terminal and BR to ground terminal. I never saw it fire. The brake did not fire, but the indication on the display was that the dynamic brake was turned on. So instead of trying to wrap my mind around that and figure it out, we just got us a new drive. Now what I did so that I didn't have to hand document the parameters, I just took the control board off the original drive and the original I/O display board, and I put in this drive we got off of the internet. So for all intents and purposes, this is the original drive. The base is not the same, of course, but the parameters are the same. So it should just go back into the machine, get hung on the wall, and act like the original drive. Okay. Woo. All right. Here are the waveforms of U and V. And on the display of the drive, it says we're running at 140 hertz. And here the fluke says we're running at 140 hertz. Let's spread this out a little bit. Let's see if we can see that PWM, pulse width modulation. Here's the high side of U to V, and here's the low side, with ground being in the middle. Let's leave it right there at 1 millisecond per division. Okay, I'm going to stop the drive. I'm going to move the leads from U to V to U to W. Enabling the drive again. All right. U to W looks the same as U to V. That's good. Stopping the drive again. And we're moving from U to W to V to W. Enabling the drive to run. Excellent. All the waveforms look the same. That's a good sign. We got a good running drive right there. I'll show you the hookups when we get home so that you can test your Berges drive. Let's see if we can run a motor. That's U. Here is V. And lastly, W. Okay, so on terminal 7, 8, and 9, I have a potentiometer. 7 is analog ground, 8 is a speed reference input, and 9 is 10 volts DC supply for that potentiometer. On 10 and 11, that's drive enable. I've got that jumped out right here. Now 14 and 16. 14 I think is digital ground, and 16 is run forward. I might have those backwards. I'll have to check the paperwork, but I got an on-off switch right there. Now, let's go apply our line voltage and we'll run this motor. Let's make sure I'm turned off. Okay. All right, in the display, it says 1.1. Now, if we didn't have this drive enable jumped out, it would say 1.1 off. Right now, it shows our frequency is at 0.0 hertz. Let's bring our speed pod over here so I can get to it. Enable the drive to run. Okay, let's give it some speed. There's 30 hertz right there, 30.5 hertz in the display. Now, this drive is a spindle drive, and we're running an inverter motor. So I don't want to run it above 60 hertz. Otherwise, we'd have too much slip. And what would happen is the motor would stall. The motor would not run. There's 54 hertz right there. That's as fast as I'm going to go. But it's running good. Nice and smooth. Slow down a little bit. There's 24.6 hertz in the display. Alright, we got us a good running drive there. We get done running this for a little bit, we'll go over and look at the original drive and you can see what all's inside there. Phew, that's a nightmare. So just run for a little bit. Here's the power base. Now on this stand-up card right here are the 6 firing channels that drive into the gates of the IGBT, and the IGBT is underneath here. Over here is the power supply section. This board right here is the switching circuitry for the switch mode power supply. And we can't see down inside it, but I've had these transistors right here that drive into the switching transformer. I've had these transistors right here short out before. Now I'm not sure who's looking at the DC bus and getting confused. I'd have to take this out, and someday I might do that in the future when I don't have anything else to do. I might go and try and figure out why this circuit is saying that the dynamic brake is firing and alternating between 1.1 off, dynamic brake, 1.1 off, dynamic brake, repeatedly doing that on the LCD of the display. Here, this is the board from the internet drive that we just ran over there. And here is our I/O connections right here. Here's the LCD. But I wanted to use the original, this drive's I/O board and control board. I'll show you the control board in a second. I wanted to use this one because it was original to this drive right here. So I swapped this internet I/O board, moved it from the internet drive over there and installed this drive's I/O display board. Also did the same. This is the internet's control board right here. I removed it from the internet drive over there and installed this drive's original control board. Right here's the processor. Here's some memory. This memory right here is a battery backed up memory. So it's something that I really don't understand, because some drives you'll get in the shop, it won't have this memory right here. This socket will be empty. So in those cases, I'm not sure where they stored the parameters. There's no battery on this unit right here. And there must be some storage memory inside the microcontroller. I'd have to look up that part number to see. But there you go. Now this board sits right here. Let me move this, the fan wires out of the way. This board sits right here. And the display I/O board plugs in right here. The power board, the circuitry for the power supplies and the signals to go down there and fire the IGBT, and the analog signals coming back up, monitoring different things. That comes up this ribbon cable into the control board. And of course, the display board, it sits in, let me get turned around right. Yeah, this would be right. It sits right here like this. Or it might be backwards. Not sure. Anyways, that's how it all goes back together. The cooling fan over here, it plugs in right here. And this is 24 volts, comes back up from the power supply. This is just a little jumper board right here to bring the 24 volts out to the cooling fan. Three-phase bridge is down on this side of the board, and it's not a standard three-phase bridge. It's a three-phase SCR diode bridge rectifier. There we go. That's the insides. Like I said, I might go in and figure out why this drive is failing, but it's in the power base. There we go. Y'all have a good day. Enjoy the time with your families. And when I get home, I'll show you the hookups for this drive so you can make your Berges ACM-D2 get up and go. See you then. All right, we're at the house, and we're going to look at the connections to make your ACM-D2 11 kW drive run. Now this is also for the 22 kW drive. The nice thing about the Berges drives is most of the hookups are identical. Now here, terminal 7 is our analog ground. Terminal 9 is our 10 volts out to provide a voltage to terminal 8. Now when our wiper is closer to ground, we're at 0 speed. And when our wiper is closer to 10 volts, we're at max speed. Now on this drive, the frequency was from 0 hertz to 600 hertz. That's moving pretty fast. Now here on terminal 10 and 11, this is our enable. And when we jump terminal 11 to terminal 10, that drive is enabled. It's ready to run. All it needs is a forward or reverse command to go. And that's provided with terminal 14 being our digital common connected to terminal 16. Now, terminal 15 we did not test, but terminal 15 is programmable, as well as terminal 16. Terminal 16 could either be stop-start, and terminal 15 could be forward-reverse, but in our case, terminal 16. Jump to terminal 14, we could run that motor. Let's go look at the relay outputs. There's 3 relays that provide information of the drive's condition to the machine. Here on terminal 19, that's relay common. That's the common of all 3 of these relays right here. And we have the K20 normally open contact to terminal 20, the K21 relay normally open contact to the 21 relay terminal. getting confused there. The K22 normally open contact to the 22 terminal. Now these are programmable. You can set them up as alarm, at speed, running, all kinds of various conditions that you want your machine to be looking back at that drive and saying, okay, here we are, this is what's happening. Now let's go over and look at the power connections, the line in, the brake, and the motor. Here's our power connections. Now on L1, L2, and L3, I applied 300 volts AC 3-phase to these connections right here, and that powered up the drive. And down here, I used a 1.5 horsepower squirrel cage induction motor manufactured by Baldor, connected to U, V, and W. Now this is a spindle drive. And I used a squirrel cage induction motor. If I ran that frequency greater than 60 hertz, we would have too much slip, and this motor would not rotate. You would have no torque because the magnetic field, the magnetic rotating field, would be too great for that motor's design. So I didn't want to go greater than 60 hertz. And it was just a visual indication to us that that drive was running correctly. Does that make sense? Now I do have a spindle motor in the shop. I just didn't want to hook it up. It's easier for me to drag this little motor around than that large spindle motor. Getting old. So the brake. This BR terminal right here goes to an IGBT that's mounted on the heat sink. And if we wanted to employ that brake, the drain of that IGBT is connected to that, and the emitter connects to bus ground. So we would take, let me draw that in here. We would take a resistor and connect it to bus plus right there, and this would be our regenerative braking resistor external to the drive. And when the motor was rapidly stopped and that energy from that spindle motor dumped back onto the DC bus looks at there's a monitoring circuit that looks at the DC bus and says, hey, we're too high. And the regenerative braking resistor pulse width modulates that too high of energy through the regenerative braking resistor to bus ground and dissipates that excessive energy into the atmosphere as heat. And when the DC bus is back to normal, then the brake is turned off. I hope that made sense. It made sense in my mind. Alright, there we go with the hookups. Alright, there you go. There's your hookups. And I hope this is a very easy drive to hook up. You won't have no problems hooking this drive up and making it go. Thanks all. I really thank you for coming by. It means a lot to me when y'all come by for a visit. Thank you very much. I can't say that enough. We'll see you in the next one.